Hello students, this is Professor Gina and I am going to do some example problems for section 8.3. We've been talking about trigonometric functions and now we're going to make a connection between trigonometric functions and imaginary numbers or polar coordinates. There are slides posted on Canvas, and so for these sections I'm just going to do a number of example problems. So for the first problem, we're going to take a given imaginary number and we're going to graph it. Let's graph the number 6 plus 3i and find its absolute value. Absolute value, if you remember, typically means distance from 0, but because we're talking about a two-dimensional space here with an x and a y axis, absolute value in this context is going to be distance from the origin. When we talk about imaginary numbers, we have the x and the y axis are slightly different. Remember that in the number that I've just written there, the 6 is the real part and the 3 is the imaginary part. And when we have our x and y axis drawn this way, the x-axis will be the real axis and the y-axis will be the imaginary axis. So we're going to move 6 spaces in the direction of x. I'll just go by 2's. And then we're going to go 3 spaces in the direction of y. So in this context, our point is going to be here. That's going to represent the point 6 plus 3i. So we're just using 6 for the x coordinate and 3 for the y coordinate. Now, when we're wanting to find the absolute value, what that's asking us is what the distance is from the origin to that point. So we've technically got a triangle that we could draw, and we're using the Pythagorean theorem to find that absolute value. So the absolute value of 6 plus 3i is going to be the square root of 6 squared plus the square root of 3 squared. We're taking both of the components, the x and the y component, squaring them and taking the square root to find the length of that hypotenuse. So this is 36 plus 9, or square root 45, which simplifies to 3 root 5. That'll be the answer for the length of that vector. Eventually we'll put this in the context of vectors. So let's do a second example like that. Let's graph negative 2i and find its absolute value. Because negative 2i is strictly an imaginary number, it's going to be on one of the axes. So if I count by 2's, negative 2i is going to be down here. Positive imaginary numbers will go up the y-axis and negative are going to go down. We could rewrite this number as negative 2i and then have a 0 in front of it, right? The real part is 0. So when we're thinking about taking the absolute value of negative 2i, we're really saying, well, the x-coordinate is 0 and the y-coordinate is negative 2. So we end up with the square root of 4, or 2. And looking back at my graph, this answer makes sense because I can see that the distance from the origin here is a distance of 2, right? Going from here to here is a distance of 2. So that answer makes sense. For our next examples, we are going to change back and forth between rectangular notation and trigonometric notation. Now, rectangular notation is like what we were looking at, where we can see the x and the y coordinate in the imaginary number, whereas trigonometric notation takes into account the angle. So looking back at the examples that we just had, there is an angle that is created right here when we make this, when we draw where that point is. And then similarly here, there's an angle that goes all the way around. This angle would be 270 degrees, right? So let's find the trigonometric notation for -10 times the square root of 3 plus 10i. So this is in rectangular notation where we can see the x coordinate and the y coordinate. Now there are a couple of formulas that we're going to use to change back and forth. We're trying to get to something that looks like this: r cosine theta plus I sine theta. R is the absolute value, right, or the length of the vector. This is going to be the absolute value of a plus bi. And then theta is the angle that's created when we figure out where that point is, and starting from the positive x-axis and going counterclockwise like we have been doing for trig. Just another note is that we typically will shorthand this into r CIS theta. The cosine I sine is, this is the shorthand version. So looks like we need to find r to start. So let's use the formula that we had from above. R is going to be the square root of a squared plus b squared, or -10 root 3 squared plus 10 squared, and we'll take the square root of that whole thing. When I square -10 times the square root of 3, -10 squared will be 100, and then square root of 3 squared will just be 3. So I think I'm looking at the square root of 400 or 20. So I think r is equal to 20. That's the length of the vector that we're thinking about. Now I have to find the angle. And looking back at the, let's actually draw a picture for where this is. And because the x coordinate is negative and the y coordinate is positive, it looks like we're in the third quadrant, right? So we've got a point that's maybe like this, where this distance is -10 root 3, and this distance is 10. And so we can use either sine or cosine, and now we know, we just figured out the hypotenuse. We know that this length is 20. So we can use either the cosine of theta is equal to a over r. Remember that this is a, in terms of a plus bi, right? Our imaginary number is a plus bi. Or we can use that the sine of theta is equal to b over r. Remember that this length is b, the imaginary part. Rearranging these, we have that a is equal to r cosine theta, and b is equal to r sine theta. These are different formats of the same equations that we sometimes use. So let's take what we have here, and we know that the cosine of the angle that we're looking for, the angle we're looking for is here, cosine of theta is going to be -10 root 3 over 20, which simplifies to negative square root of 3 over 2. The sine of that angle is going to be 10 over 20, or 1/2. So when I think about my unit circle, I know that the angle that has a cosine of root 3 over 2 and a sine of 1/2 is 5 pi over 6. So theta is either equal to 5 pi over 6 or 150 degrees, depending on whether you're looking at radians or degrees. So the original imaginary number that I had was this. And the trigonometric notation for this is r, which is 20, and then cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. Or you can write it as 20 times the cosine of 150 degrees plus I times the sine of 150 degrees. If we were to multiply this back out, if we were to say find the cosine of 150 degrees and then multiply it by 20, we would get -10 root 3. And if we were to multiply sine of 150 times 20, we would get that 10i. So multiplying that back and forth is how you can get to the imaginary number. All right, let's do one more example like that. Let's find the trigonometric notation for -5 plus 5i. This looks like this one is also in the second quadrant, right? So my point is going to be here. I know that this distance is going to be -5 and this distance is going to be 5. I'm thinking that just based on the picture that I've drawn that this is going to be a 45-degree angle, right? So I'm kind of thinking that theta is going to be 135 degrees just based on the picture that I've drawn, but let's use the formulas to verify for ourselves. So we want to start by finding r. R is going to be the square root of a squared plus b squared, or -5 squared plus 5 squared, which is 25 plus 25. So r is square root of 50, which simplifies to 5 times the square root of 2. Okay. Then we'll figure out the sine. So let me draw that there. This is 5 root 2. The sine of theta is going to be b over r, or 5 over 5 square root of 2, which is going to simplify to square root of 2 over 2, right, if I rationalize the denominator. Cosine theta is a over r, or -5 over 5 root 2. So that'll be negative square root of 2 over 2. So as we suspected, the angle is 135 degrees, or 3 pi over 4. So writing our final answer, we have that -5 plus 5i can be written as 5 times the square root of 2 times cosine 135 degrees plus I times the sine of 135 degrees, or 5 times the square root of 2 times cosine 3 pi over 4 plus I sine 3 pi over 4. Right, I'm going to pause and get a new piece of paper. Be back in just a second. Okay, I am back, and let's do one more example similar to the one that we just did. This time what we'll do is we'll find the trigonometric, notation for 7.5 times I. I'm going to tackle this in a slightly different way, just thinking about where this point is rather than using all of the formulas. This is a strictly imaginary number. We could write it as 0 plus 7.5 I, where the real part is 0 and the imaginary part is 7.5. And so we know that this is going to be just on the y-axis here. This is where 7.5 I would be. And we can already see the distance from the origin. Remember that the distance from the origin is r, so just by looking at the picture, we can say that this distance here, we can say that r is going to be equal to 7.5. We can go through the whole formula, square root of a squared plus b squared, but we're still going to end up with 7.5. And then we can also use those formulas we had before to find the angle using sine and cosine, but I can see by looking at the picture that the angle is going to be 90 degrees, right? Just by looking at it. So I'm just going to shorthand this one and say that 7.5 I is the same as 7.5, which is r, cosine of 90 degrees plus I times the sine of 90 degrees, or 7.5 cosine pi over 2 plus I times the sine of pi over 2. Now, just to kind of show you what's happening, I'm going to consider this first version here. Let's look at 7.5 cosine 90 degrees plus I times the sine of 90 degrees, the trigonometric form. And if I found this and I wanted to know where that was in a graphing perspective, I would just think about what the cosine of 90 degrees is. The cosine of 90 degrees is 0. The sine of 90 degrees is 1. Right? So that's pi that's multiplied there. And then I've got this 7.5 on the outside. So you can see that what's ending up happening is I'm just ending up with 7.5 I, which was what we were given originally. So going back and forth, going the other direction is a little bit easier because you're just going to multiply things out. And that's what we'll do next. Let's find the standard notation or imaginary notation. A plus bi of 6, and I'm going to put the shorthand, cis 120 degrees. When I write the shorthand version, that means 6 times cosine of 120 degrees plus I sine 120 degrees. When you're in calculus, they'll shorthand it all the time. So just like I did in the last example, I'm just going to think about what the cosine of 120 degrees is, which is -1/2. And then I'm going to think about what the sine of 120 degrees is, which is square root of 3 over 2. And both of those are going to be multiplied by 6. So 6 multiplied by -1/2 will be -3. And then if I multiply 6 by square root of 3 over 2, I'm going to get 3 times the square root of 3. So 6 cis 120 degrees is the same as -3 plus 3 square root of 3 times I. Let's do another like that. Let's find the standard notation of 3 cis 0 degrees. It's interesting, right? 3 times the cosine of 0 degrees plus I sine of 0 degrees. If I were to draw where this is, 0 degrees is going to be on the positive x-axis, right? And it looks like that distance is going to be 3, so I'm thinking that the point is just going to be there. That looks like 3 plus 0I, or just the number 3. Let's calculate out here. The cosine of 0 degrees is 1, and the sine of 0 degrees is 0. So when I multiply that by 3, yeah, the I is just going to go away, and I just end up with the number 3. So 3 cis 0 degrees is just the same as the number 3. All right, last one of these type. Let's find the standard notation of 5 cis pi over 3, or 5 cosine pi over 3 plus I sine pi over 3. The cosine of pi over 3 is 1/2. And the sine of pi over 3 is square root of 3 over 2, right? So 5 times 1/2 will be 5 over 2. And then I'll have I multiplied by 5 root 3 over 2. So I think that 5 cis pi over 3 is the same as 5 over 2 plus 5 root 3 over 2 times I. All right. For our next examples, we are going to look at multiplying and dividing these numbers together. And so we have a couple of formulas to consider. I'm going to talk about the formulas first before I get started. We're going to consider two of these trigonometric numbers, and I'm going to denote them with subscript. Subscript is a little number that's written down below, kind of the opposite of an exponent. And so this first number that I've written, I've put a subscript of 1 just to say that's the first number. So the R is sub 1 and theta sub 1, just so that I know that it's the first of those two measurements that I'm talking about. And then we'll look at a second number, R sub 2. This is our second number, and it has a potentially different angle, so we'll put sub 2. When I have two numbers like this that I'm multiplying together, it's actually quite easy in that I'm going to take the two lengths or the two absolute values, and they get multiplied together. So that'll be R1 times R2. And then I take the two angles and I add them together. So, oops, I didn't make enough room here. So I'll take theta 1 plus theta 2. Theta 1 plus theta 2. Now, the reason that we think about this is that sometimes when we have imaginary numbers, and especially you'll see in an example I'm going to do in a little bit, when we raise them up to a power, it's really time consuming in the multiplication. And if we switch to trigonometric form, it actually makes those calculations much easier. So sometimes when we're in trigonometric form, the calculations become simpler. So let's do an example. Let's multiply 5 cis pi over 3, using the shorthand notation, multiplied by 2 cis pi over 4. So using the formula that I had above, I'm going to take the 5 and the 2, and they get multiplied together. And then I take the two angles, pi over 3, and I add to pi over 4. I just add the two angles and multiply the two absolute values or lengths of the vectors, and then I add the two angles. So I think my answer is going to be 10 cis. So pi over 3 plus pi over 4 is going to be, let's see, we have 4 pi over 12 plus 3 pi over 12, 7 pi over 12. That's our answer. Division is really similar. If I want to take a number and divide it by another, I take, oops, that should be a 2. I take the two absolute values and I divide them. And I take the two angles and I subtract them. So let's do an example like that. Let's divide 1/2 cis 2 pi over 3 by 3/8 cis pi over 6. So I can grab a calculator to do the first part. I'm going to do 1/2 divided by 3/8. And that's going to end up giving me 4 over 3. So I'm going to have 4/3. And then I'm going to take 2 pi over 3 minus pi over 6, which is the same as 4 pi over 6 minus pi over 6. So that looks like 3 pi over 6 or pi over 2. So I think that my answer is going to be 4/3 cis pi over 2. Now, I kind of referenced that the time that this is really useful is when we're raising a trigonometric number to a power. So if I had a number like, let me draw a line here just to kind of denote something different. Suppose that I had 3 plus 2 square root of 3 I, and I wanted to raise this to the 4th power. I would have to multiply this out 4 times, right? And so it would be this lengthy process of multiplying it twice, and then multiplying it again, and then multiplying it again, right? This would take me a really long time. But instead, if I change to the trigonometric format, then this formula that I'm about to give you makes it easier. So changing to the trig notation makes this easier. The formula that we're going to use is that if I have a number in trig form that I'm trying to raise up to a power, I'm going to raise the absolute value number up to the power. And then I'm just going to take the angle and multiply it by whatever that number is that the power is. This is a lot easier than multiplying out multiple times, right? So let's do an example. Let's look at 2 cis 120 degrees raised up to the 4th power. If we were to think about this in its imaginary format, it would be, let's see, 2 cosine of 120 degrees is -1/2, -1/2. And sine of 120 degrees is square root of 3/2. This would have been -1 plus square root of 3i raised to the 4th power. This would be sort of the alternative to what we would be doing. And this is a lot more difficult. We have to multiply this out 4 times. Instead, what we'll do is we'll raise 2 to the 4th power. That's easy. And then we'll take the 120 and we'll multiply it by 4. So it looks like we've got 16. And then we've got 480 degrees. To finalize our answer, what we're going to do is we're going to take the 480 degrees and just bring it back between 0 and 360. So let's subtract off 360 degrees, which will bring us to 120. So we're ending up with our answer as 16 cosine I sine of 120 degrees. Interesting that that ended up with the same angle, right? That doesn't always happen. It just happened in this particular example. Let's do one more like that. Let's look at 2 plus 2i raised to the 4th power. It's kind of what I was saying. This format makes it really complicated. I've got to multiply that out 4 times. But instead, what I'll do is switch this into trigonometric form. So this will switch into, let's see, 2 and 2. This is going to be a 45-degree angle here. And the length of that vector, or r in this case, is going to be 2 squared plus 2 squared, or 2 times the square root of 2. So in trigonometric form, this is 2 root 2. This 45 degrees. Just change that from the picture that I had. So instead, we are raising this to the 4th power. So if I take 2 times the square root of 2 and I raise it up to the 4th power, I'm going to take each of these and raise them to the 4th power separately, or you can just type this into your calculator. 2 to the 4th power is 16. And then the square root of 2 to the 4th power, I'm going to have 2 times 2, which is going to be 4. So I'm going to get 64 here. And then we're going to take 45 degrees and multiply it by 4, which is 180 degrees. So I think that 2 root 2 cis 45 degrees raised to the 4th power is going to be 64 cosine I sine of 180 degrees. Now let's multiply this out. 64 times cosine of 180 degrees plus I times the sine of 180 degrees. Cosine of 180 degrees is -1. Sine of 180 degrees is 0, right? So it looks like my overall answer, remember what I was doing originally was I was looking at 2 plus 2i raised to the 4th power. And my final answer is -64. If I were to multiply all of those out 4 times, a bunch of the i's would have canceled out, and I'm ending up with this as my final answer.